This educational video has been brought to you by Chromperfect, the leading independent chromatography data system. In this video we will be using Chromperfect to demonstrate the topics being discussed. We will also review some academic images which are fairly low resolution. These are not indicative of Chromperfect output. However, they are useful to demonstrate some of the points of discussion. If you would like more information about our software, please visit our website at www.chromperfect.com or call 97358685551. Chromatography Theory, Chapter 5. Calibration Theory. This chapter explains the process of creating calibration curves. The use of calibration curves in the process of calculating amounts from peak areas or heights are covered elsewhere. Here we assume that peak detection, integration, and identification have been satisfactorily performed by the integration algorithm, so that the peak areas and heights are known. Calibration curves are created by fitting a selected kind of curve to a set of data points. Each data point has two values, an amount and a response. By fitting the calibration curve to these points, we obtain a formula, the formula of the calibration curve. This formula gives the response as a function of the amount, and hopefully will accurately predict the detector response for intermediate amounts. Readers are forewarned that this chapter contains more mathematics than any other, and mathematical terms are frequent throughout. For example, mathematicians consider straight lines to be one particular type of curve, and so we will use the term curve to refer to what is obviously a straight line. Following common practice in mathematics tests, this chapter posits a series of calibration models, starting with a simple model and developing more complex models as new features are introduced. These models are meant to represent real laboratory situations, but the actual numbers used were chosen to illustrate particular features. For example, peak areas are often round numbers. This of course would never happen in real laboratory chromatograms. Choice of units. Despite their importance to quantitative analysis, units are strangely absent from Chromperfect. While the calibration file does contain a unit field, this has no effect on the numbers generated, but only serves as a label for amounts on the reports. The reason for the apparent absence of units is that they are arbitrary. If the calibration file is set up in a consistent manner, results may be reported in mass units, nanograms, concentration units, micromoles per liter, or dimensionless units, weight fraction, with equal ease and validity. The amount units are the units of the values in the amount fields for each component. Except for internal standards, described below, it is normal for all components in a calibration file to use the same amount units. However, it is not necessary for them to do so. External standard models. We begin with models that assume that external calibration method is used. The complications of internal standard calibrations will be treated separately. To perform an external standard calibration, one must prepare a standard stock solution containing all the components of interest. This stock solution is appropriately diluted, and aliquots of the diluted stock solution are injected. As the peaks emerge, the detector response is recorded in a raw file. The application may require only one injection, or it may require multiple injections using the same or different dilutions of the standard solution. Each injection generates a raw file, and these are processed in the usual way. Each injection is used to update one level in the calibration file. There is a data point for each component and each level. The response field of each data point is set to the detector response for the peak in question. The amounts are unchanged and remain at the values set by the creator of the calibration file. Single-point linear calibration. To begin, we will assume that the response of the detector is proportional to the amount of material emerging from the column at that time. We seek the constant of proportionality, or response factor. This number will differ from one component to another and from one day to another. Since proportionality is assumed, only a single data point is required. The calibration curve for one component is shown in the following figure. This calibration curve was created from a single injection, containing 5 micrograms of this component. In keeping with the assumption of strict proportionality, the calibration curve drawn through the points is a straight line through the origin. The slope of this line is the desired constant of proportionality. In this example, that number is 1000 divided by 5 equals 200, and the formula for the calibration curve is y equals 200x, where y represents the response and x the amount. In the illustration above, the amount is specified in a mass unit, micrograms, but the amount could be specified in terms of concentration as well. In theory, if the injection volume is not excessive, the detector will respond to the mass of each component, rather than its concentration. In practice, however, chemists often prefer units of concentration. The two systems are equivalent if the injection volume is held constant, and for the present we shall assume that this is the case. Replicate point linear calibration. The calibration curve in the previous example reflects the detector response to a single injection, and implicitly assumes that the measurement of the detector response was accurate. Of course, if the same dilution of the standard stock solution were repeatedly injected, each raw file would yield a slightly different estimate of the response. By giving each of these injections its own data point, the calibration curve may be made to reflect the average detector response, which may be assumed to be a better estimate than given by a single injection. This calibration curve was created from 4 injections, each containing 5 micrograms of this component. The 4 data points have the same amount, and therefore lie in a vertical line. As can be seen in the expanded plot on the right, the calibration curve does not pass through any point, but passes through the average of the 4 points. Replicate points are mathematically equivalent to the averaging update feature that Chromperfect supports, where a single data point reflects the average of several injections. However, the use of replicate points is recommended because of the practical advantages. All the injections are shown, so that outliers may be easily spotted. The calibration file will contain a complete audit trail, and the average error will give an indication of the inherent precision of the method. Multi-level linear calibration. The models described above are single-level calibrations, which assume that the detector response is proportional to the analyte amount. This assumption is regularly violated in the laboratory. The detector response may be nonlinear, and even when it is linear, it may not pass through the origin. We will discuss the linear case first and consider nonlinear curves afterward. To dispense with the assumption of proportionality, that is, that the calibration curve passes through the origin, there must be data points at more than one amount. If calibration is performed at several amounts across the range of interest, then any significant deviations from proportional response will be apparent. Replicate points at each amount are acceptable here, but are neither necessary nor, in themselves, sufficient. Apologies are extended in advance for any confusion that may arise from the fact that the several levels in the calibration file may refer to the same, or different, amounts. Consider the calibration curves in the following figures. Here the calibration curves are straight line that passes exactly through the 2 data points, but not the origin, which is completely ignored in the process of curve fitting. Therefore, the relationship between amount and response is linear, but not proportional. The formulas for these calibration curves are y equals 105 times x minus 40, and y equals 95 times x plus 40. The fact that the calibration curve does not pass exactly through the origin has implications for quantification at low levels. When the calibration curve intercepts the y-axis below the origin, a peak with zero area would be assigned a positive amount. When the calibration curve passes above the origin, small peaks will be assigned negative amounts. At first glance, it would seem that non-zero intercepts are always undesirable. Sometimes this is true, and, as described later in this chapter, Chromperfect offers several ways to avoid them. However, sometimes non-zero intercepts, particularly positive intercepts, are legitimate. Consider the case where there is significant detector noise in the chromatogram. The effect of this noise is to depress the baseline, causing an increase in measured peak area or height that is largely independent of peak size. It therefore acts to raise all the data points by the same amount. The calibration curve, a line through these points, is raised by a similar amount, which we see as a positive intercept. Therefore, when confronted with a positive intercept, one should estimate the amount of excess response that may be contributed by the noise. When quantifying by height, this is approximately equal to the peak, not peak-to-peak, noise. When quantifying by area, this is equal to the product of the peak noise and the baseline peak width, in seconds. The peak noise is difficult to measure but is usually less than 3 times the RMS noise. Therefore, the formulas for estimating excess response are: for height 3 multiplied by RMS noise, in microvolts. For area 3 multiplied by RMS noise, in microvolts, multiplied by baseline peak width, in minutes, multiplied by 60 seconds per minute. If the intercept is less than this value, then there is no need to look further for the source of the positive intercept. If the intercept exceeds this value, then some other cause may be operating. Measuring the precision of calibration. The multi-level models described above have only 2 data points, and the calibration line passes exactly through both points. In general, it is not possible to draw a straight line through 3 or more points. In such cases, it is necessary to fit a regression line to the data points using least squares techniques. This line will not pass exactly through any of the data points but will come as close as possible. The following figures illustrate such a calibration curve. Chromperfect supports 3 ways to measure what statisticians call the goodness of fit, that is, how close the regression line comes to the data points. These are the coefficient of determination, the average error, and 2 related measures, the average calibration factor and the percent relative standard deviation of the calibration factors. The coefficient of determination. The coefficient of determination is a statistical measure of how well the calibration curve fits the data points. A value of 0 indicates no correlation, and a value of 1.0 indicates that the calibration curve passes exactly through each data point. For a linear fit, the coefficient of determination is equal to the familiar linear correlation coefficient, r squared. When the fitted curve is a quadratic or cubic polynomial, coefficient of determination is equal to the multiple correlation coefficient, r squared. The concept behind these measures is the same. Coefficients of determination are commonly provided either as the value itself, or as the square. In all cases, Chromperfect provides the square. A weakness of the coefficient of determination is that it is normally between 0.99 and 1.00 for chromatography calibrations. It has no units of percent error and gives little intuitive information. If the calibration involves replicate points at a single level, then the coefficient of determination is always 0. In this case, the average error and the RSD, described below, are more indicative of the quality of the fit. When the calibration curve is the power fit curve, then the coefficient of determination refers to the r-squared value for the underlying linear fit to the logarithm of the areas, or heights, as described below. When the calibration curve is point-to-point, no least squares fitting is performed, and the coefficient of determination is not reported. The average error. The average error measures the average vertical distance of the data points from the curve. The percent error of a data point is defined as the deviation of that point from the calibration curve, measured vertically and expressed as a percentage of the value of the curve at that amount. Percent errors are negative if the point lies below the curve, and positive otherwise. The average error for the curve is the average of the absolute value of each data point's percent error. Average errors are never negative. If the curve passes exactly through every point, then the average error is 0. The average error gives an intuitive indication of the precision of calibration. For instance, if the average error is 3%, then one may expect at best about 3% precision in any analysis using this calibration curve. When the calibration curve is point-to-point and there are no replicate points, the average error is 0. This is an artifact of point-to-point calibrations and should not be taken as a realistic estimate of precision. The average calibration factor. The calibration factor, average calibration factor, and the percent residual standard deviation are terms that relate to a calibration that uses a straight line through the origin, defined in ASTM 8000. These measure errors as deviations from a strictly proportional relationship, which may or may not coincide with the calibration curve. The calibration factor, CF, for each data point is simply the ratio of the response to the amount for that point. It is equal to the slope of a straight line drawn through the origin and the data point. If the detector response were perfectly proportional to amount, then all these lines would have the same slope, but normally there will be slight variations. The average calibration factor for the curve as a whole is the average of the CF values for all data points. The formula for the average calibration factor is shown on screen, and is the average of the slopes of lines drawn from the origin to each data point. The percent residual standard deviation, RSD, is the standard deviation of these slopes, divided by the average slope and expressed as a percentage. The formula for the variance of these slopes is the sum of the squares of the deviations, from the average calibration factor, of these slopes, divided by the number of points less 1. And the formula for the RSD is the square root of the variance, divided by the average calibration factor, multiplied by 100. As described below, it is possible to use the average calibration factor line as the calibration curve. However, this measure of fit is available even when other types of calibration curve are employed. Weighting the data. When fitting a curve to a set of data points, each point may be given a weight in addition to its x and y values. In the examples given above, all the data points have equal weight. If the weights are unequal, then the fitted curve will pass closer to the points that are more heavily weighted. Statisticians weight their data according to the relative amount of error associated with the data points. The more precisely a data point is known, the heavier the weighting it is given. When the errors in the data are independent of the response, they are said to obey Gaussian statistics, and are frequently referred to as instrumental errors because they originate with the instrument that generates the signal. Detector noise falls under this category. Equal weighting is most appropriate in this situation. When the errors in the data are proportional to the response, they are said to obey Poisson statistics, and are frequently referred to as statistical errors. Errors due to variations in sample preparation or in injection volume fall under this category. Consider a calibration curve with two levels, with amounts of 1 and 10 micrograms, and peak heights of 10 and 100 millivolts. When the injection volume is 10% high, the peak heights will also increase by 10%, so they will be 11 and 110 millivolts. The error is the difference, namely 1 and 10 millivolts. In absolute terms, the smaller peak is more precisely known. Therefore, it is most appropriate in this situation to weight the data points inversely proportional to the response. Chromperfect supports 5 types of weighting, shown on screen. Only the first 2 types have any formal mathematical justification. Inverse square weighting is like inverse weighting in its effects, but more extreme, and is preferred when inverse weighing does not give the desired effect, as is sometimes the case when the range of the data points, amount or response, as appropriate, is less than 100. Some users find it convenient to use 1/x or 1/x squared weighting because it simplifies checking the results by hand calculation. When the response is proportional to the amount, then 1/x and 1/y weighting are essentially identical, as are 1/x squared and 1/y squared weighting. When inverse or inverse square weighting is specified, the regression line will pass closer to the low-level data points, those near the origin, even if it must pass further from the high-level points. The result is a calibration curve that is more accurate at low levels, but less so at high levels. Indeed, if the calibration covers a wide range, inverse square weighting may result in a line that practically ignores the high-level points. Weighting always reduces the quality of the fit, as indicated by the coefficient of determination. The average error may change in either direction, depending on the relative spacing between the data points. In practice, weighting is seldom used for strictly theoretical reasons, but frequently as an expedient to force the calibration curve to favor the low-level data points. The following figures illustrate the effects of weighting on a calibration curve. These lines are all fitted to the same 7 data points, which have amounts of 1, 3, 10, 30, 100, 300, and 1000. The responses are almost proportional to the amounts, but there is a slight curvature in the data points. The plot on the left shows the high-level data points, but the low-level points are too close together to be distinguished. These are shown in the expanded plot on the right. The figure on screen shows the same data points with 3 fitted lines. The equally weighted line has the smallest slope, and passes close to the high-level points, but misses the low-level points and intersects the y-axis at a response of 340. The 1 divided by y weighted line passes less close to the high-level points, but closer to the low-level points, and intersects the y-axis at a response of 48. The 1 divided by y squared weighted line, blue, passes close to the low-level points, intersecting the y-axis at a response of 15. This line misses the high-level points and has a significantly larger slope. Origin treatments. As noted above, multi-level calibrations usually ignore the origin, so the calibration curve does not pass exactly through the origin, and quantification at low levels may be adversely affected. Weighting of the data may reduce this problem but will not eliminate it. Chromperfect supports 2 ways to address this issue. Each component in the calibration file has an origin field, which may be set to ignore, extrapolate, or force. If the origin field is set to ignore, then the calibration curve is the usual regression line, as described above. See the figure in the section, Measuring the Precision of Calibration. The figures in this section use the same data points, only the origin treatment has been altered. If the origin field is set to extrapolate, then the calibration curve has 2 linear segments, using the usual regression line for medium and high levels. For amounts less than the amount of the lowest level point, it uses a straight line between the origin and the line. This scheme has the advantage that the calibration curve is optimal at high levels, but it suffers from a discontinuity in slope at the lowest amount, where the 2 lines intersect, as shown in the following figures. The coefficient of determination, the average error, and the average calibration factor are not affected by extrapolation to the origin. These measures apply only to the main calibration curve, not the auxiliary segment. If the origin field is set to force, then instead of the usual regression line, the calibration curve will be the best line that passes through or near the data points, and passes exactly through the origin. Therefore, the intercept will be exactly 0, as shown in the following figure. The force calibration curve is smooth everywhere, but compared to the usual regression line, it passes less closely to the data points. This is particularly true of points that are close to the origin. It is not uncommon to see large % errors for such points. The lowest point, at amount equals 1, in the figure above has an error of 49%. The coefficient of determination is adversely affected by forcing the curve through the origin. This curve has a coefficient of determination of 0.988, down from 0.997 for the usual regression line. The average error is also adversely affected. This curve has an average error of 24.3%, compared to only 8.8% for the usual regression line. The average calibration factor is unaffected. Forcing or extrapolating the curve to the origin gives the most satisfactory results when the effect of the option is small, that is, when the unforced calibration curve passes close to the origin. When developing a calibration method, it is best to start with the unconstrained curve. Once the correct degree and weighting are found, and the accuracy of the calibration verified across the expected range of values, then the force or extrapolate options may be selected so that quantification will be satisfactory at low levels. The average CF calibration curve. Some analytical methods mandate that the calibration curve be a straight line through the origin, with a slope equal to the average calibration factor of the data points, as defined in ASTM 8000. The formula for the average calibration factor appears earlier in this chapter. The average calibration factor calibration curve is identical to a linear curve, forced through the origin, with 1/x squared weighting. Nonlinear calibration curves. The calibration models discussed so far have all used linear calibration curves. Any deviations of the points from this line were assumed to be due to measurement error, not to inherent nonlinearity in the detector response. Like the assumption of proportional response, this assumption is regularly violated in the laboratory. Real detectors are often nonlinear over part or all of their useful range. A nonlinear calibration curve will compensate for detector nonlinearity and extends the range of accurate quantification. Chromperfect supports three types of nonlinear calibration curves: the quadratic, the cubic, and the power fit curve. Theory does not indicate which of these is the best. The choice is a qualitative decision and must be made on a case-by-case basis. Except for their curvature, these calibration curves are similar to linear calibration curves in many aspects. They may use replicate points, and the coefficient of determination and the average error have their usual meanings. However, the average calibration factor and RSD are not meaningful. In particular, the reported RSD value may be large enough to cause concern to users who habitually use this measure to judge the quality of fit. Points and polynomials. Before discussing nonlinear calibration curves, a brief discussion of the theory of polynomials is necessary. Polynomials are characterized by their degree. The degree of a polynomial is the highest power in its mathematical expression. A straight line has the general formula y equals a multiplied by x plus b. Since x is raised to the first power, straight line is a first-degree polynomial. Similarly, a quadratic or parabola is a second-order polynomial, having the general formula y equals a multiplied by x squared plus b multiplied by x plus c. And a cubic is a third-order polynomial, having the general formula y equals a multiplied by x cubed plus b multiplied by x squared plus c multiplied by x plus d. Polynomials are useful as calibration curves because they have bends that may match the nonlinearity of the detector. A polynomial of degree n has n-1 bends. None for a straight line, 1 for a parabola, and 2 for a cubic. These bends are also the source of certain complications that will be discussed below. The maximum allowable degree of the fitted polynomial is related to the number of distinct points, i.e., points with different x values, not replicate points, in the calibration. It is always possible to draw a straight line exactly through 2 points, but not 3 or more, except in the unusual case where all the points happen to lie on a straight line. For this reason, we say that 2 points define a straight line. Similarly, it is always possible to draw a parabola exactly through 3 points, but not 4 or more, and we say that 3 points define a parabola. A polynomial of degree n can be drawn exactly through n plus 1 points, but not more. Forcing the curve to pass through the origin increases the number of distinct data points by 1. The maximum allowable degree of the fitted polynomial is similarly increased. For example, a parabolic fit may be made with only 2 calibration levels if the curve is forced through the origin. If an attempt is made to use a polynomial that requires more data points than are available, Chromperfect will issue an error and refuse to create the calibration curve. To continue, the user must reduce the degree of the polynomial, force it through the origin, or add more levels. When there are more than the required numbers of distinct points in the calibration, the polynomial will pass near, but not through, the points, and it is necessary to fit the curve to the data points using least squares techniques. It is preferable to have an excess of points for several reasons. A low-degree polynomial is usually sufficient to accurately model most detectors. Such a polynomial will not fit the points exactly, but the scatter around the curve will give an indication of the inherent precision of the method. A high-degree polynomial that fits the points exactly will often exhibit large excursions between the data points, rendering it unsuitable for quantification. Examples of these problems appear below. The quadratic, parabolic, calibration curve. A parabola is a polynomial of degree 2, so it requires at least 3 distinct points, or at least 2 if forced through the origin. It has a single bend, which can mimic a nonlinear detector response along part of its entirety. Two views of a typical parabolic calibration curve are shown below. This curve passes close to, but not exactly through, the origin and the 5 data points. The plot on the left shows that the slope of the curve decreases with increasing amount. Within the range of the data points, this curve is well behaved and may be expected to give accurate results. The plot on the right shows the region beyond the range of the data points. The slope continues to decrease with increasing amount, eventually becomes 0 at the apex, and then becomes negative as the curve turns over. The detector, of course, does not behave like this. The curve is useless beyond the apex, not only because it has ceased to accurately mimic the detector response, but also for a purely mathematical reason. When the response is greater than the height of the curve at the apex, then one cannot use the curve to calculate an amount. One may find the point on the y-axis corresponding to the peak area, but moving horizontally across the graph fails to meet the calibration curve. The amount and response corresponding to the apex of the parabola are referred to as the critical amount and the critical response for this component. When calculating amounts from responses, the integration algorithm will use the calibration curve when the response is less than the critical response, but if the response exceeds the critical response, the integration algorithm will report the critical amount and set the overrange flag. This indicates that the actual amount is not known, although it is greater than the critical amount. This is the most information that can be obtained with this calibration curve. Every parabola has an apex, so every parabolic calibration curve has a critical point. Ideally, and in many practical situations where the detector is almost linear, the critical point is far from the data points and the issue of turnover never arises in practice. When the detector is quite nonlinear, however, the critical point may draw near to, or even move into, the range of the data points. If the critical amount is not at least 150% of the highest data points amount, then a warning will be issued. This is not an error. The user may elect to save the calibration file and use it as is. Occasionally, an inverted parabola is encountered, as shown in the following figure. It is unlikely that this curve accurately mimics the detector response, and a warning will be issued. Curves like this are usually due to an error of some kind. The cubic calibration curve. A cubic is a polynomial of degree 3, so it requires at least 4 distinct points, or at least 3 if forced through the origin. It has 2 bends, and, like the parabola, can mimic a nonlinear detector response along part of its entirety. Compared to the parabola, the cubic curve offers a better fit within the range of the data points, at the price of a poorer fit outside that range. Unlike the parabola, which always turns over once, the cubic curve either turns over twice, or not at all. Therefore, the cubic curve can appear in a variety of forms and may or may not have a critical point. Two views of a typical cubic calibration curve are shown below. This curve passes exactly through the origin and the 3 data points. Except for the asymmetry, it is quite similar to a parabola. Like a parabola, the curvature increases with increasing amount, up to the critical point. This is a weakness since the actual response of most nonlinear detectors has less curvature at high amounts. When the data points reflect this situation, the cubic curve will reflect this curvature, as shown below. Here the curvature is greatest at low amounts and decreases at high amounts. In fact, as the plot on the right shows, the curve straightens out and eventually reverses its curvature at the inflection point. Therefore, this curve does not turn over and does not have a critical point, so it may be used to quantify a peak with any response whatsoever. However, as the positions of the data points change, a critical point may appear. The following figure shows an overlay plot of 4 cubic calibration curves, one identical to the above and the other 3 identical except that the highest point, not shown on the lower curves, has been moved to progressively lower responses. The second curve from the top has a nearly horizontal region, but no critical point. The 2 curves at the bottom turn over twice before resuming their upward trend. These curves do have critical points and the critical amounts are near 3.0. Like the variations in weighting discussed above, slight variations in one of the data points may significantly affect the behavior of polynomials outside the range of the data points. If the curve is not forced through the origin, then the origin lies outside the range of the data points, and the intercept may be similarly affected, causing inaccurate quantification at low levels. The power fit calibration curve. The power fit curve is not a polynomial. This curve mimics the response of many detectors over a wide range and has several advantages over polynomials. It never turns over and has no critical point, it always passes through the origin, and its curvature decreases with increasing amount. The formula for this curve is of the form y equals a times x raised to the power of b, where x is the amount, y is the response, and a and b are the fitted coefficients. The curve always passes through the point x equals 1, y equals a, and b represents the slope of the curve through this point. Normally, b is in the range 0.7 to 1.0. If b equals 1.0, then this formula reduces to a linear calibration curve that is forced to 0. If b equals 0.5, then this formula describes the square root function, and its curve is a parabola lying on its side. If b greater than 1, then the curve is concave upward, which is always inappropriate. The power fit curve is fitted to the data points by fitting a straight line to the logarithm of the amounts and responses, rather than to the values themselves. Because the power fit curve always passes through the origin treatments are unnecessary. Data weighting may be used, but usually has little effect because the range of the data in the log domain is small. 2 power fit calibration curves are shown below. The curve on the left has its calibration points evenly distributed, and the fitted curve is well behaved. In the curve on the right, the points are confined to the highest levels, and generate a statistically correct but physically inappropriate calibration curve. If used for quantification, such a curve will have significant error at low levels. The apparent extrapolation to the origin is an artifact of plotting the curve that vanishes as the curve is magnified. The main disadvantage of the power fit curve is its behavior near the origin. Although it is not easily seen in plots, the slope increases without limit as the curve approaches the origin. At the origin, the curve is vertical. This will cause the integration algorithm to underestimate the amounts of small peaks, but in practice this error is insignificant. The point-to-point calibration curve. The point-to-point calibration curve is, in the strict mathematical sense, not a curve, but a series of line segments with common end points. In the absence of replicate points, these segments connect the origin and adjacent points in the calibration curve. When replicate points are present, the segments connect the origin and the average of the replicate points for each distinct level. The last segment is continued beyond the last data point, allowing quantification outside the range of the data points. Because this curve always passes through the origin treatments are unnecessary. Because each distinct level is treated independently, data weighting is inappropriate. A typical point-to-point calibration curve is shown in the following figure. Troubleshooting problems with curve fitting. Occasionally, one may obtain a calibration curve that does not meet expectations. Certain curve problems cause warnings whenever the calibration file is saved or printed, and whenever the user moves to the Statistics tab section. The following table lists the warnings and describes when and why they occur. Average calibration factor and point-to-point never generate warnings. Only the first warning is reported. Other problems that may be present will not generate warnings until the earlier problems are fixed. Therefore, the first thing to do is to adjust the settings until the warnings cease. If there are no warnings, then the following suggestions may reveal the source of the problem. First, check the data points in the component spreadsheet. The amounts should be positive numbers, spaced at regular intervals, perhaps farther apart at high amounts. The responses should be positive numbers, roughly proportional to the amounts. Next, examine the plot. There should be a plotted data point for every level in the calibration file. If you cannot see them all, then some may be so close together that they are drawn on top of one another. Expand the plot to see these. If some are still missing, then perhaps some data points are inactive. Return to the component spreadsheet and see if any amount cells have a green background color. Those that do will not appear in the plot. To activate a point, double-right-click on its amount cell to remove the background color. If all points are present, check their positions on the plot. If a single data point seems too high or too low, then perhaps the wrong peak was identified, or a baseline is incorrectly drawn. Examine the corresponding bound file. If everything looks right, print out a standard report and verify that the peak response is correct. If several points are amiss, then perhaps the wrong files were used to update one or more levels. Go to the Statistics tab section and select the problem component. Select the level list box and examine each level in turn, paying particular attention to the source and date. If a data point was not updated, perhaps it is frozen. Return to the component spreadsheet and see if any response cells have a red background color. Those that do will not be updated. To unfreeze a point, double-right-click on its response cell to remove the background color, then update that level again. If the points appear correct, make sure that the curve properties, fit type, weighting, origin treatment, are correct. Theory of internal standards. An internal standard is a compound that is added to each sample and serves as a reference for quantification of the other materials in the sample. To be effective, the compound chosen for an internal standard must meet several criteria. It must have a retention time that is different from all materials in the sample, so that its peak will not overlap others. It should be chemically stable under the conditions of sample preparation and analysis and should give an adequate detector response. When using an internal standard, it is the ratio of peak responses that is of interest, rather than the responses themselves. For this reason, the injection volume does not enter the equation. Any amount may be injected as long as the column is not overloaded, and the detector response is adequate. Calibration solutions are prepared containing known amounts of the components as well as the internal standard. The standards are injected, and the chromatograms integrated in the usual way. The response of each analyte peak is divided by the response of the internal standard peak, and the response ratio is plotted against the ratio of amounts. Finally, a calibration curve is fitted to the calibration data points. For the simplest case of a single point calibration and a straight line through zero, the slope of the calibration line is slope equals AA multiplied by RI divided by RA multiplied by AI. Where AA is the amount of the analyte, AI is the amount of the internal standard, RA is the response of the analyte peak, and RI is the response of the internal standard peak. Internal standard calibration curves are identical to external standard calibration curves, except that the former tend to have smaller numbers on the y-axis. Everything in this chapter that used an external standard calibration as an example is also applicable to internal standard calibrations. Chromperfect supports multiple internal standards. However, each component in the calibration file may refer to only one other component as its internal standard. Internal standard units. The amount of internal standard may be specified in the same units as the amounts of the analyte components, or in completely arbitrary units. Some chemists find it useful to define a standard unit of internal standard equal to, say, 1 milliliter of solution. This expedient is perfectly acceptable since the internal standard is not included in the total amount and amount percent calculations. If the calibration file contains more than one internal standard, an arbitrary unit is necessary unless all internal standards are added in equal amounts. Thank you for watching. If you enjoyed this video, please hit the like button and subscribe to our channel for more YouTube chromatography content and training videos. You might also want to follow Chromperfect on Facebook and Twitter. If you would like to receive more information or a demonstration of Chromperfect, please contact our sales team by visiting www.chromperfect.com or call 973-586-8551.